Okay, let's dive right into this explainer and explore the fascinating physical engineering that really dictates a robot's durability and mobility. When we think about advanced robotics, it is so easy to get completely distracted by the flashy software, the complex code, or the artificial intelligence. But without the right structural foundation, all that brilliant software is quite literally going nowhere. So today, we're breaking down the absolute bedrock of robotics.
Here's our roadmap for today. We're going to cover 1. The glass robot problem, 2. Exoskeleton versus endoskeleton, 3. The material trade-off, 4. Real-world robot bones, and 5. The ultimate design challenge.
All right, part 1, the glass robot problem, a truly shattering start.
Imagine a news clip showing a multi-million-dollar, highly advanced robot just shattering into a million pieces during a basic stress test. Yikes, right? It forces us to ask a really basic question. Why aren't robots made of glass? Well, it perfectly illustrates that raw material choice is literally a make-or-break decision for any robotic build. I mean, sure, glass might be rigid, but it completely lacks the toughness to absorb impact. If your materials can't handle the physical stress of the real world, your robot just becomes a very expensive pile of debris the moment it trips over a wire.
Moving on to part 2, exoskeleton versus endoskeleton, setting the foundation.
Before we start cutting metal or pouring plastic, we really need to understand the architectural foundation of a robot. You can't just pick your materials until you know how your structure is fundamentally built. And at the core of all this architecture is the chassis. Basically, the chassis is the physical skeleton. It completely dictates the durability, mobility, and overall performance out in the field. If you get the chassis wrong, the motors aren't going to align, the weight distribution will be totally off, and the entire system will just fail to do its job.
So engineers are forced into a critical choice right out of the gate. Do you protect the outside or do you support from the inside? Think of an endoskeleton like us, like the human body, an internal support frame where the components are mounted on the outside. Now contrast that with an exoskeleton, kind of like a beetle or a crab, which relies on a really tough external support frame where all the delicate, squishy components are safely housed inside. Each choice dramatically changes how the robot moves and, crucially, how it absorbs damage.
Next up, part 3, the material trade-off. Let's build that toolkit. Once you've nailed down your frame style, how does a roboticist actually step through the material selection process? Look, no good engineer just grabs a solid sheet of metal on day one. There is a very logical, step-by-step build pipeline. Step 1 is almost always cardboard. It's cheap, it's super easy to cut, and it's absolutely perfect for testing basic geometry and prototyping. Step 2 is plastic or PVC, which gives you that functional durability to test movement without, breaking the bank. And finally, step 3 is aluminum, providing the actual operational strength you need for the final build.
But hold on, because here is where we need to bust a massive myth that trips up almost every amateur builder out there. The false belief that metal is just inherently better. I get it. It sounds logical. If you want a tough robot, build it out of solid steel, right? But as we're going to see, stronger is definitely not always better. In fact, defaulting to the strongest metal can completely doom your design right from the start.
Relying purely on metal completely ignores critical engineering trade-offs. You have environmental factors like maybe you need a material that won't rust. You also have strict weight limitations. Heavy steel might require motors so massive that the robot literally drains its entire battery in 3 minutes flat. And specific functional needs absolutely outweigh raw strength. Think about it. If your robot is too heavy to even lift its own arm, all that strength is totally useless.
All right, part 4, real-world robot bones. Time to put this theory into practice.
Say you're building a BattleBot. You have a massive choice to make here. You have to weigh the heavy defensive juggernaut capabilities of steel against the lightweight mobility of wood. I know, wood sounds completely crazy for a combat arena, but actually, it absorbs kinetic impact incredibly well without permanently bending, and it leaves you with a massive weight allowance to invest in bigger, faster motors and way deadlier weapons. It is the ultimate test of function over pure strength.
And sometimes achieving a specific function means thinking entirely outside the metal box. Take James Bruton's Open Dog project as a great real-life case study. Machining metal into the intricate, complex shapes required for dog-like joints would have been way too heavy, insanely expensive, and just far too rigid. So 3D printing allowed for rapid prototyping and perfectly balanced lightweight components to pull off a really specific function, like four-legged walking.
Which brings us to part 5, the ultimate design challenge. Let's test your knowledge.
Matching the exact material to the specific functional need is essentially the hallmark of a great roboticist. So let's categorize what we've learned so far.
Aluminum is the perfect pairing for a heavy rover that really needs to survive rugged, rocky terrain. Plastic? That's your absolute go-to for a lightweight drone where literally every single gram affects your flight time. And cardboard, of course, remains the undisputed champion for the concept prototype.
Let's do a quick mental exercise. If your robot needs to swim, what is the absolute worst material you could choose, and why? Well, think back to those environmental factors we just covered and ask yourself how water would instantly ruin certain heavy or porous materials. Cardboard? That's going to turn to mush in seconds. Heavy steel would just sink like a stone and rapidly corrode. No, for this, you'd absolutely need buoyant, waterproof plastics or highly sealed, lightweight alloys.
Let's push it one step further with some guided practice. Imagine you're designing a chassis for a robot that must carry a 5-pound brick. Keeping those weight limitations in mind, how would you combine the strength of an endoskeleton with materials that won't just buckle under a 5-pound payload? You probably wouldn't use cardboard here for sure, but solid steel might be total overkill. So, a sturdy aluminum internal frame combined with an outer plastic shell, that would give you the perfect balance of payload capacity and efficient movement.
I want to leave you with this one final thought to ponder as you look at the machines around you today. How do the very bones of a robot completely define its destiny? The materials we choose dictate whether a machine can fly through the air, crawl over rough rubble, or navigate the deep ocean. The foundation is literally everything. Thank you so much for joining me for this explainer, and the next time you see a robot in action, I really hope you take a closer look at the bones that make it all possible.